So we were looking at, so 1 second. So we were looking at the, yeah, we were looking at this graphs of functions, and we were trying to make sense of area under them. Many deep questions can be asked, and non-calculative questions as well. Integration, obviously, it's very popular as a computational thing. Interesting as well. So we wanted to make sense of the area under this. Okay. So make sense of area under F. I'm not defining, you understand what F is. I'm not saying F is continuous, just like this. Okay. So can anybody give a review of how we went there? Yes, right. So we made partitions of A to B. So what we did is we made regular partitions, right? So we said you take an epsilon. So just to summarize that, we took regular partitions. I'm just using the word regular. It's also a standard word, I suppose, meaning partition in which parts have the same size. And for every partition, we kind of took an upper sum, the upper approximation of what we want to be the area. And we know what we want the area to be. We know that. So for every partition, we made an upper approximation, we made a lower approximation for every regular partition. Because regular partitions is easy to describe and so on. And then we said, okay, now you make finer and finer partitions. And then the upper sums will kind of decrease and the lower sums will increase. And if they converge to the same thing, as epsilon becomes small, epsilon goes to 0, then we define that converging thing as the area as it should be defined, as it should be defined. Right? So let me just write that in short. So we have epsilon greater than 0, and then we made this partition. So don't worry, I'm not going to go into refinements and so on today. That is not, there is some fundamental things which I want to address. So because there are a few things I said last time, which is actually turns out to be maybe, let's see if it is. So we took like this partition, which is A. So you understand what I mean by this, means these are the cuts, the endpoints. And you assume that it kind of becomes B at some point. We took this partition, and for this partition, we took this what is called an upper sum. Okay. It's very important to understand this clearly. Again, I'm using this notation today. I kind of used last time also, I think. So just to say it very clearly, what is this? So for each part, okay. So for the ith part, we pick fmi, okay, where mi is equal to max of f of a I epsilon to I plus 1 epsilon, right? In that interval, right, in that part, a I epsilon to a I plus 1 epsilon. In that part, we had to take the maximum. So in this case, it is just the end, kind of like the end point, it's the end point basically, or you take supremum maximum. I understand. And obviously this will just be epsilon. That's a good thing. That is a good thing about taking regular partitions, right? So we have this. So it's very interesting. The sum of the values of the function is kind of also becoming constant, finite. This was the upper sum. Similarly, we had the lower sum. Let me write that along here only. I'm not going to describe this now. You understand the lower sum. Okay. Then obviously we know that the upper sum is always bigger than the lower sum and so on, right? For every partition and even for any two different partitions. Okay. So let's write that clearly. So if epsilon 1 is bigger than epsilon 2, then we know that u of p. Yes, I have not. That's a mistake I made, right? I should maybe put epsilon here. So then I'll put epsilon 1 here. Okay. Partition corresponding to epsilon 1. Not such a good notation. Yeah. So let's call this epsilon here only. Then it's better notation. But it's not about u, it's about the partition. So we have u p of epsilon 1 f, right? This. So as you decrease the epsilon, what will happen to the upper sum? It's going to decrease, right? But it will obviously be bigger than the corresponding lower sum. But the lower sum increases when you decrease the epsilon, okay? Because minimum over smaller sets is bigger. Okay, so obviously we say that if u of p epsilon f, limit of this, if the upper sums converge to the same place where the lower sums, then they should converge to the same place. Otherwise, we will not want to say that region has an area. Okay, so if the upper sum and lower sums converge to the same thing, then we say that it has an area. Okay, then we say that f is integrable. I mean, that's a definition. So integrable and equal to this quantity, obviously is equal to. All good things are squeezed between two things. That is the. This was just a summary, basically, of more or less what we did the last time. Okay. So you have to take regular. So the way we are doing, we are taking regular partitions and we are showing that the upper sums and lower sums end up in the same place. Okay. Right. But usually if you open the textbooks, you will see that this is not the way it is done. They take all partitions. They don't take only regular partitions. I think if you see Rudin or even Spivak, I think, not remembering about Spivak, but Patil and Sherbet, they deal with the situation for all partitions. So then what is my definition? Is it wrong? What does it mean to be wrong? What is happening? Okay. How is it different? Is it equivalent? What do those things even mean? So they can be made into good problems. So let us look at this. So this basically means this last thing, meaning that the upper and lower sums converge to the same thing. Oh, so it's just join. Okay. Okay. So then I think today we will. I think so. Let's leave it at this summary today. Okay. I will just tell you. So I just wait just 2 minutes. Okay. Yeah. I thought you would join at 11, but I think you think it got updated. It's good. So okay. So we will just. So let me just give a summary of what are the questions. Okay. See, this thing that the upper sum and lower sums become the same. This basically means that for any delta, okay, for any delta, there is some epsilon, right? Such that this thing becomes less than that delta, right? But I am so there is some epsilon, so there is some regular partition for which it becomes less than delta. Okay, but if you're doing the theory over all partitions, then you will only be showing that there is just some partition for which it becomes less than delta. So that seems like that's a more powerful theory, right? Because you are having you can take any partition for any delta, you will find some partition for which this happens. But we only have a regular partitions to do. So whatever is integrable in our sense, if some function is integrable in our sense, then it is definitely integrable in that sense when all partitions are allowed. Okay?
No.
Yes. Yeah, just 2 minutes. 2 minutes. Okay. Yeah. So if something is integrable in our sense of regular partitions, which means that for any delta, we are able to make the difference between upper and lower sums less than delta using this kind of partition, then obviously I can use that in the set of all partition. But in the usual definitions, all partitions are allowed. And so it seems like that is more powerful, right? So it seems like maybe for some function, there is some delta for which some partition works, but then that's not regular. Okay, so then what happens is that there is a partition for which you can make it less than delta. So then it becomes integrable in this sense. Okay, but if there is no regular partition which will do it, then it is not integrable in our sense. Can that happen? Okay, the answer seems to be no, that these are equivalent theories, but we will see that the next time. Oh, no. Uniform continuity is a little, what analog? They maybe, I'm consistent, no. What analog do you mean? No, but they are same for closed intervals. Oh, no, but this is slightly different. No, this is slightly different. For this delta, we want a partition, right? Now, whether you can do with, if there is some partition, some very good partition which you can use to avoid bad points, and so you can use a partition. But can you find a similar partition in our theory? It seems like the answer might be no, because our set of partitions is more restricted. We will show that it is not the case next time. Okay, I will say this again next time, because this will lead to a very, I'll frame it as a concrete question, as a very elementary problem actually. But this answers this thing that the theories are saying. Okay, I'll do this next time. Okay, so we'll just stop now. Okay, sorry. So we'll surely do this continue this on Thursday, surely. Okay. Thank you. I'll take the question next time. Okay, thank you. Bye. Yes. Hello.